Hello, my name is Jeff Franklin. I am the original architect and lead developer for the CFD software tool called Azore. Azore is a software tool for solving practical engineering problems. You can find out more about Azore at the website azorecfd.com. And there there's a lot of information about it. You can download a free trial. I encourage you to go over and take a look at it. Today, we're going to talk about surface integrals and what the appropriate way of taking surface integrals. We're going to look at an example of taking a surface integral for temperature, and also we're going to look at a more complex example of total pressure. So let's start taking a look at this. The first thing we want to do, I want to kind of talk about is for every CFD project, we have, we kind of go through this pipeline, and I think it would be a good idea to kind of quickly talk about that. And so basically a CFD project begins with a project proposal. This is where you kind of outline what you want to do with the CFD project. And once you have done that, then you go through it's technology pipeline where you maybe use software engineering, intuition, and the likes of that to solve a particular problem that you have outlined in your project proposal. And hopefully by the time you're done doing, applying all of these techniques over here, you have some useful information to get a satisfied customer. And this kind of applies to a wide range of people, whether you're applying CFD in-house for the technologies that you have, or you're using this as a consultant for a wide array of industries. The important part of this is to set up the problem and make some good decisions, and the more good decisions you make early on in the process, the more smoothly the later sections and the applications of the technology will go. So I think we'd be talking a little bit about that first before we dive into the surface integrals and focus in on the subject of this thing. So here's an expanded view of this technology pipeline. Here we have our project proposal, and this is probably one of the most important aspects of starting a CFD project, is where you really want to outline what you want to do in your project. You want to outline it, and you want to take into consideration all of these other tasks that are going to be done. So in your project, when you set up you want to understand what is the geometry in my CAD tool that I am going to use. Then that way, when you get to the point where you're applying that, you have a good idea. And then you also want to have up here decided on what kind of meshing techniques you're going to use. How dense is your mesh going to be? Then when you get down here, you have your simulation set up. What physics am I going to have in there? That all of these things kind of depend on one another. So like your CAD geometry depends on your project scope, your domain, and your meshing also depends heavily on how your CAD is done. And so you need to really take in consideration what meshing techniques you're going to use when you prepare your CAD, and so on and so forth, all the way through the whole project pipeline. And it's good to have all of that stuff outlined and put forward in your project proposal before you go on to it. So that's kind of the project pipeline, and we talk about these in these CFD technology discussions. We kind of focus in on one of these aspects today. So today we're really going to focus in on, we're going to talk about total pressure in terms of the surface integral, and that kind of falls in the area where we're post-processing our results and we're reporting our results, and we want those to go back, and we should know what we want to get out of it, and then hopefully we'll get the information to get to a satisfied customer. So let's take a look at that. Before we dive into the total pressure, I kind of want to back up and say, what really is a surface integral? We have our CFD information, but we want to do a surface integral, and a surface integral is basically uses a list of surface facets that are kind of cut through our CFD prediction to calculate some sort of average engineering value using some type of weighting value. So we have these discrete values on our surface, we weight them by some value, and then we get an average value. And the trick is what weighting value is the appropriate value to use for a particular value? How do we make a decision on what those weighting values are? And maybe we should just take a quick look at that first. Well, first of all, what do we want it to do? Well, the weighting method should it should be really tightly connected to the physics of the engineering quantity being evaluated. What are we really interested in? The weighting method should be consistent with the conservation equations. We certainly want to make sure that we conserve momentum, we conserve mass, or whatever other thing that we're conserving in our CFD simulation. We want to make sure that the surface integrals are, you know, they represent what you would expect for these quantities. So maybe to get our feet wet with this, maybe we'll start by picking some sort of an example. And I think temperature is one that we maybe can kind of relate to easily, more easily than maybe total pressure. So let's just start with that. And what kind of a weighting method would really be appropriate for something with conservation of energy? So the weighting method, it really should be consistent with the conservation of energy. It should be applicable because in CFD, the flow is going to be kind of passing through a surface. But it's one thing I would like to note here is temperature is not something that's conserved. There's no such thing as conservation of temperature. There's only conservation of energy, and temperature variation really is kind of a consequence of conservation of energy, and that's really what we want to make sure that everything is consistent with that when we do our surface integrals. So to do that, maybe we'll just kind of pick a simple example to kind of look at this. And the example that I've chosen is just this T-duct, where we have some flow coming in on the left-hand side of the T-duct and some flow coming in here. It joins together and then it leaves out on the right here. And one thing I've shown here is, CFD predictions often come in these filled contours where they were kind of continuous, but here I've shown the CFD predictions on a cell-by-cell basis. All CFD predictions are basically a bunch of point data, and that's really what you need to mine. You're going to look at all this point data, and you're going to mine it to try to extract engineering information. And so this depiction of the CFD prediction kind of highlights that. Like right in here in this area, we're kind of assuming that all of the value in this area on average is representative of what would happen, or what the velocity would be in this particular image at this location. So this is the example we're going to use, and we're going to look at the temperature. So let's look at the temperature here. Here what we've kind of set up is we're going to say, well, let's just say that a low temperature comes in on the left-hand side of our T, and a high temperature comes in here, and then we'll watch it mix, and then it'll leave right over here. We're going to use air, and just to make things simple, we're going to use a constant density, a constant specific heat, and this AI value is kind of the area of each one of these cell faces down here, so that'll help in our calculations. And then we're going to assume that there's going to be no energy loss through our walls, so it's kind of adiabatic. So the only energy is just a combination of energy. We have energy coming in here, we have energy coming in here, and then we have energy leaving over here. Some other relationships that would be interesting and useful as we evaluate that is the enthalpy. And for this example, we're just going to use a simple relationship for enthalpy that is simply the specific heat times the absolute value, the temperature here. And then we have the mass flow rate, which is the mass flow rate through one of these surfaces right over here is the sum of the density times the velocity times the area for each one of these cell faces. So with all of this information, we can kind of calculate the amount of energy entering here and the amount of energy entering here, and then we can look at the amount of energy leaving here. We can kind of calculate that even before we run a CFD simulation. Our CFD simulation over here are some of the numbers. So like right here, we can see that our CFD simulation predicted a temperature at the top of 573 degrees, and then it got a little cooler, 509 and the 304. So those are our CFD predictions on the exit plate of that, along with the velocity values, basically 0.5 meters per second and then growing up to 1.2-ish meters per second. So that's kind of the flow structure that we have here, and we kind of want to know what is the average temperature at this location. What is it going to be? We're going to use our surface integral to kind of gather up and determine what that value is. So how do we do that? Well, we want to make sure, first of all, we kind of calculate this. Before we run the CFD simulation, we don't need a CFD simulation to tell us what the average temperature is here. We should know that in advance, and we can find that simply by energy balance. And so I've kind of expanded out the energy balance. So like the energy passing in this surface right here, well, we can find the mass flow rate, which is basically the area times the velocity times the density, and then we have our, and that gives us our m dot, and then we can find out the enthalpy of that mass coming in, which is basically our specific heat times the temperature, and it gives us basically a joules per second entering here. And we can do a similar calculation down on our cold side, gives us another, joules per second entering our domain. And once we know those two numbers, we can actually come over here and add them up, and we can come up with how much energy is actually leaving this system right here. And then once we know that, we can use our relationships to come up with what maybe the appropriate temperature would be there that conserves, that represents the conservation of energy. So we can simply take the amount of energy leaving based on conservation of energy, divide it by the mass flow rate. We know the mass flow rate here because we know the mass coming in here and the mass coming in here. So we can divide that out, and so we can find the enthalpy of the fluid leaving here, and then using our enthalpy relationship, we can divide by the specific heat and come out with what the temperature is, the average temperature that represents conservation of energy. And it kind of makes sense. It's between the value of, our 300 degree and our 600 degree temperatures here, and the mass flow rates are the same, so it's kind of the mean. So that's kind of what you would expect, and everything's good. So now we know what the temperature should be, but we want to use some sort of, in our CFD tool, we want to use some sort of area weighted method to find out what this value should be, and what should that be. So for temperature, the appropriate one is a mass flow rate weighted number here. That's the correct choice. And so if we do those same calculations, it would be for each one of the surfaces on the exit, we would take the density at each one of the surfaces, the velocity, the area. And this velocity is, of course, normal to the surface multiplied by the temperature. And then if we do all that math, it comes out to 450 degrees K. Is exactly what it represents that. Everything's good. We're happy with that number. But I thought maybe just for example, what would happen if we decided, I'm going to use area weighted. And if we did the same thing using area weighted, we would actually end up with an estimated average temperature at the outlet of 475 degrees K. And note that like this temperature, it really doesn't honor the conservation of energy here. And that is not good. I mean, that is not really representative of what our engineering expectations would be. So area weighted average, I mean, these values this might seem physically realistic. It is certainly between the 300 and the 600 number, but it could be misleading. And if you were simply using a CFD tool and using an area weighted average, and you didn't know what the expectations were, and you were perhaps shooting for a temperature of 450 degrees, and you were doing some design work, you might be tempted to go back and say, well, actually my CFD tool is telling me that I need to change the temperature on my inlet or the outlet and adjust it to get my 450 degree temperature. And then if you used area weighted, you could get a 450 degree temperature there if you adjusted it. The problem is if you went out into the field and you implemented this, practically speaking, you're not going to get that, and that's problematic. And so it's important in our CFD tools that we use the appropriate weighting method for the values that we're looking at. So that kind of covers a simple example with temperature, but total pressure is a little bit more complicated. And so this is a discussion of how to deal with surface integrals of total pressure. And I kind of have outlined what we're going to talk about here. First of all, maybe we'll just talk a little bit about what total pressure is. It's kind of basically two terms that kind of characterize a fluid streamline. And then we'll talk about really what needs to be conserved along this streamline, conservation of forces, momentum along a streamline. Then we'll talk about how to average between these streamlines to come up with some sort of surface integral. I'm going to introduce this concept of conservative total pressure, which is an average of a total pressure value within a CFD tool. And then at the end, we're going to kind of look at an example problem with some comparisons similar to what we did with the temperature. So let's get into it here. So like the first thing we want to look at is the momentum equation. And the momentum equation is basically force is equal to mass times acceleration. But if we kind of break that down and we go through a derivation, we can quickly use Bernoulli's relationship to come up with this relationship of momentum along a streamline, which is basically says that the static pressure plus the dynamic pressure, which is the velocity squared over 2 times the density, plus hydrostatic force, that will be constant along a streamline if there are no other losses in the system. And that's a very useful relationship, and that's kind of the foundation of where this total pressure expression comes from. So this is what we're really trying to conserve, is conservation of momentum along a fluid streamline. So here we're keeping track of this kinetic energy, and for the total pressure, it's typical to say, well, actually this changes the effects of gravity. We're really not that interested in it. We're really kind of only interested in the relationship between the static pressure, which is the forces along our fluid streamline, as well as the velocities along the streamline. So we're going to just basically kind of assume that this is 0 and it's small and we're not interested, and we're going to just group these two terms of the momentum equation together, and we're going to call them total pressure. And that's really what total pressure is, where the V refers to the velocity along the streamline, P refers to the forces kind of perpendicular to the streamline, but along the streamline. The density refers to the fluid density along the streamline. And if there are no losses along the streamline, then this total pressure will remain constant throughout the whole streamline. So that's kind of what we're doing here, and those are the physics of what we really want to enforce if we're using some sort of averaging technique for total pressure. So let's kind of dig into this a little bit more. So let's just look at one fluid streamline that starts over here. It kind of passes through here, but we're going to say it kind of passes through some sort of surface. And how can we come up with a value? If there are no losses, as I've said, that it's going to be constant. If losses are present, then the total pressure will decrease. It will always be decreasing here. So this would be the highest value, and it's always going to get smaller and smaller as it goes along out to this point, except for if there's something in our system, like say for instance, we had a fan in our system. Then we have added energy into our system, so we would expect that the total pressure would go up. If we add heat to our system, then we would expect maybe our total pressure would go up. But static pressure really represents the fluid forces along the fluid particle streamline. So if the pressure is decreasing and there are no losses, if the pressure is decreasing, you have a high pressure here and a low pressure here, then you would expect that the velocity would begin increasing. And likewise, if the pressure were lower here and higher here, then you would expect that the velocity decreases. And so these two items right here, these two together are kind of in balance with one another. The pressure variation kind of keeps track of the forces along the fluid path line. This kind of keeps track of the kinetic energy along our fluid path line. And in terms of integration, we really want to kind of come up with a total pressure that represents that. And if we only have one path line crossing our surface, then the total pressure at this location, it's obvious. I mean, it's one value because it crosses the streamline. The problem is what happens if we have two fluid streamlines crossing our surface at the same time, right here? Then what is the average total pressure? Because now you have a total pressure here and a total pressure here. How do you average those together? Is it simply a numeric average of all the streamlines passing through there? Well, how do you determine what are the number of streamlines passing through our integration plane? We need a method to average between streamlines, really, to come up with our total pressure value. So let's just make it a little bit more complicated. Here, maybe an average between the twos might be appropriate, but what happens if the streamline is very complex? It can have a lot of bends in it, and then perhaps this total pressure here could be vastly different from these up here. And so now how do we kind of account for that? The problem is streamlines can be very complex, especially if you have a cutting plane that cuts through a 3D geometry, a 3D flow structure that can be quite complex. So, and it becomes less straightforward about what these streamlines look like. Well, let's add it just a little bit more complication here. What if our streamline crosses our integration plane many times? Here we have a streamline is crossing 1, 2, 3, 4. It's 5 times. So how do we come up with an average value along this plane that accounts for the fact that our streamline has passed through there many times? We need to make sure that we come up with an averaging method that is going to be consistent with our engineering expectations about what is going to happen with total pressure at a system level. Well, let's even make it a little bit more complicated. In CFD, we can make surfaces of any shape we want. We can have a surface that is not even planar like this. So we also need integration techniques that really account for the changes in the geometry of our surface that we're using for integration. So we really need an integration technique that kind of covers all of these aspects. So total pressure surface integrals. Really a total pressure is really kind of a vector quantity in some sense. They're along a streamline rather than a scalar quantity. CFD tools display total pressure. You can look at them as a filled quantity and it is a scalar value, but really that contour of total pressure is a cutting plane, and it is a bunch of total pressures from a whole bunch of fluid streamlines. It is not a conserved quantity like temperature, for instance. And so because of that, typical averaging techniques like area weighted, mass rated, mass flow rated really are not appropriate for total pressure. They can give you deceiving results. And that's one aspect. Azore really uses these, has methods that give us values that are consistent with our engineering expectations. So in Azore, it has surface pressure, which we call conservative total pressure, and this is an averaging method. It's kind of a name for this averaging method. It kind of distinguishes it from some of the other methods that we have out there. So here is the averaging technique that is used for total pressure. And you can kind of see here is basically, here is our total pressure term, but the averaging it takes into account the area. So we have a faceted geometry that we're extracting information on. And so we have an area and we have the velocity dotted with the normal of that surface. And then that's the weighting value we use for the total pressure at that particular location. So we're essentially creating a stream tube, a series of stream tubes at the resolution of your mesh at that surface, and the stream tubes that pierce that surface. And we have an area, and so they're kind of weighted by the area, the cross-sectional area of that stream tube, and the flow volume passing through that stream tube. And this weighting technique will give us very consistent results here. And that's basically the summation for all of the facets of our surface divided by the sum. This is, the numbers for this averaging technique. So now we kind of know how that is. I've kind of selected an example problem to look at these averaging techniques, and we're going to kind of compare other methods of coming up with total pressure and see how they compare to using this conservative total pressure method. So the problem I have set up right here, it's a problem that's set up in such a way that really accentuates the problems that you might have with gathering total pressure information. And I call it, it's basically, this is a rotational mixing tank where here is the inlet and the fluid is going to come in here and you're going to get some rotational motion, and then it's going to leave and there's a separation zone here. It's going to go around. And so our task here is, let's look at the total pressure, and we're going to extract total pressure at each one of these red lines, and we're going to look at what that total pressure is for this system. And we really should expect to get engineering values that don't defy our engineering expectations through here. We would expect, you know, this is going to have the highest total pressure. This one's going to be lower, 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 all the way through the system, because there are only viscous and turbulent losses in this system. We're not adding any energy to it. And that's what our engineering expectations should be for this particular case. It's contrived for sure to accentuate these problems, but it's, you know, this is a good example to kind of accentuate what I'm trying to get across here. So here's the velocity field that we would see in this, where we have a high velocity that comes in, it goes around the corner. Here's the separation zone that I kind of mentioned before. We have a little recirculation zone, and then it leaves right over here. That's kind of what the velocity field of this looks like. Let's just take a look at the streamlines here. And here is a fluid path line. If it would go, there we go. So this is what, if we were to drop a fluid particle here, this is kind of the trajectory it would take. It basically kind of crosses each one of these integration planes once. Let's look at one that's just a little bit more interesting here. Let's drop off fluid particles right on this plane right here, and let's see where they go. And you can kind of see they're going around. So something like this particle, it's kind of leaving the system right here, but these are spinning around, and you'll notice they're just kind of going in a circle. In reality, they're going to go around many, many times. It could cross this plane thousands or hundreds of thousands of times, this streamline could, before it eventually makes it out here and leaves the system. And so what kind of an averaging technique can we use that really kind of accounts for that? And that's what that total, you know, the averaging technique that we have proposed to do and account for this. So here's the pressure, the total pressure distribution that you would see here from a scalar standpoint. And this is basically total pressure on almost an infinite number of fluid streamlines. You can see right here where the velocity is high, the total pressure is high. It's lower in the middle where the velocity itself is lower, and then it goes around and then comes out here. So that's it. That's what the total pressure field would look like in this problem. So now let's just take a look at, if we were to look at our integration planes, and let's just plot it out here. So here is our inlet where it has the highest pressure, and we're going to look at it. This is our conservative total pressure. This is what we're going to start with looking at here. And this kind of goes along with what we would expect. The total pressure is highest on our inlet, and it's lowest over here, and nowhere along, basically it kind of drops monotonically all the way down. There's no point where the pressure goes below and then rises up, and which is exactly what we would expect to happen from an engineering perspective through here. Even right here where we're right in the middle of that giant recirculation zone at this plane one. So now let's look at some of the other methods if we were to use, and let's use a mass flow weighted average. Here, this is the example of how you can kind of get physically unrealistic values if you use the weighting method on total pressure of mass flow weighted average. Here you see we start with a high value, but way down here, right in the middle here, we have a very low value. And if this was the only 2 points we were looking at the system, it wouldn't really defy our engineering expectations. However, we have one more point over here, and we can see that all of a sudden our total pressure has gone up dramatically. It's dropped dramatically, and then it's gone up dramatically. And even worse, that this total pressure right here is lower than our exit total pressure. So that really kind of defies our engineering judgment. And this location right here, this is one that one would not really choose if you were analyzing a system. However, we want any tool that we use within our CFD tool to report, relevant and proper values, even if we choose a surface that is maybe not appropriate. Over here, you can kind of see where we're crossing over that secondary recirculation zone. You can kind of see it's less obvious. And this is where you could really have kind of problems if you're looking at 3D flow structures that are very complex. You can be in the situation where you're kind of trying to evaluate the pressure loss between 2 points. And you might see something like this if you use mass-weighted flow averages, and it would be confusing, maybe just a little bit, and then you're trying to decide, is that an error in my, is my model not converged? It's just not, it makes it a little grayer as to what you're looking at. So that's our mass flow rated average. The next one is our area weighted, and this one is actually even worse in terms of expectations. You can see you have the big drop over here in the recirculation zone, but here you have 1, 2, 3 points perhaps below here. So the total pressure goes way up, then it drops way down, and then it goes up again, and then it goes over here. So anyway, this area weighted, it does kind of give you physically unrealistic values for our total pressure and not really appropriate. So now here's kind of all of them put together here, and you can see the values of the velocity at the inlet and the outlet are fairly uniform, so the values are essentially the same at those locations. It's where the velocities are very non-uniform. Our fluid path lines are crossing our surface integration planes with a lot of variability that you see a lot of deviation from our mass flow rated and area weighted averaging methods one might use. So this kind of sums up the total pressure integration methods. So in summary, surface integrals are really an important aspect of CFD simulations, but we really need to make sure that we use the appropriate surface integral for the appropriate quantity that we're extracting. CFD tools allow you to define surface integration locations that can really split complex flow structures. What we really want to do is, when possible, we want to pick surface integral locations that align with typical engineering analysis. So like, we would probably not pick that plane 1 in the example that we just did, because it would be hard to even measure that. You would probably pick planes within the piping structure at different locations where you maybe would have a pressure tap where you could kind of get engineering information. The other thing is when selecting a surface integral averaging method, make sure that it is consistent with the physics that we're trying to report. We really want to make sure that the averaging technique is really consistent with our physics. In particular, when we're reporting total pressures for a system analysis, we really want to make sure that we report values in conservative total pressure. We want to use that method specifically if we're interested in total pressure values. And lastly, maybe just to kind of extend this concept a little further, we often use volume integrals within CFD tools, and the same concepts and methods that we have discussed for surface integrals also apply when we are doing volume integrals. We want to make sure that the volume integrals that we perform are consistent with conservation of mass, conservation of energy. So anyway, that kind of sums up the surface integral discussion here. Have a good afternoon. Bye.